name is Dmitry Karpov. I'm a software engineer in online game company, and today I would like to talk with you about making an online games, and actually not only online games but any real-time high-load application with Python, and solving an issues which may occur when you're using it. With online game as an example, of course. Today we will talk about what is the World of Tanks online game and other games of World of series, for example, World of Warships, World of Airplanes. Also, we will discuss motivation to use Python for that. We will discuss what is Big World cluster, and we will discuss some issues on Python. About real-time maintenance, network issues, network architecture with some examples, multi-cell via single-cell approach, and variable types in such projects with Python. And make some conclusions in the end, of course. First of all, just to let you a brief introduce what is our online game, let me show you some statistics on it. We open and close 10 arena per second. Arena is a one game session where about 30 players can play simultaneously together. About 10,000 events sent per one game session from server to client, and it is not limited by by only one client. So we send that amount of events to every client, and some of them have interception and some of them don't intercept. We have more than 1 million peak online. We have 4.5 million weekly unique visitors in European Union cluster, and we have about 200,000 most players online simultaneously on one mock server. That is a Guinness record. To prove all of these statistics, you can follow these links. And let's talk about why in such a big project we are using Python. First of all, let me show you a couple of graphs which are borrowed from that article in the bottom of the slide. It is a Pratchett et al. Work about empirical comparison of different programming languages. You see that here the two performance comparison between C, C++, and Python and other languages are presented on the slide on two benchmarks, Z1000 and Z0. It is a runtime in second for the same benchmark, and actually don't be confused. Here you can see a logarithmic scale, so every step decreases performance twice. Here you can see C or C++ performance and Python performance, which looks not so bad, but then keep in mind that it is a logarithmic scale. The remaining part of the work you can reference that work with that link after. But on the other side, Python have a great opportunity for business. The median hours to solve a problem in Python is 2.5 times better than other languages like Java or C++, and median lines to solve a problem is about 3 times better than C and C++. Here is a usual linear scale, that digit is not so much better as on the previous slide, but actually you see that in the same time we can make 3 features rather than 1 using languages with better performance. Let's get a brief overview what the cluster is. Here is a very surface schema of our cluster. You can see the packages come from the internet and go to a different application, login application or base application. Then it goes inside the cluster through different cell application, database application, cell application managers, service application. We will get an overview of them a little later. Oh, did I forget something here? Yeah, on the other side of an internet, there is our dear clients with a client application which send the packages to our cluster, and a lot of players on other side, and probably a couple of cheaters that try to hack our gameplay pretending being usual gamers. The application shown on the previous slide are here. First of all, it is a cell application. We handle all the geographical data, all the spatial data is processed there. Cell application manager is a cell application coordinator. It helps to load balance between different cells. Base application is a process responsible for different big world entities. And also it is used as a proxy between client and cell application, so that no client connected directly to cell application. Service application is just some kind of subset of base application. It is a base application, but which functionality is limited to only one function. For example, we log everything to MQ, and some process have to do that. So we allocate one base app only for that reason, and that became the service application. Base application manager loads balancing the load between service and base application. Login application creates a new connection and proxy. Database application provides database interface. Database application manager is a coordinator of DB apps. Intercluster manager manages intercluster communication. Also, we have an inspector process, and BBMeshID is a daemon which runs on every machine and helps to coordinate the whole cluster. The technology stack in that project is presented on the slide. We are using mostly Python. Also, some network code is written in Erlang. Also, we are using Scala and JavaScript. The frameworks we are using is Django, Falcon, and Synchro. We are using storages as Postgres, Percona, and Cache and Redis. So that I hope currently you have a brief overview what is the project. And let's talk about the Python in the project. Actually, here should be a total rather than gap because in real-time application we have to provide a guarantee for any client that when he made any input, he will get a response at least in 100 milliseconds, and we do not process the whole cycle more than that, because otherwise that wouldn't be a real-time application. First of all, the Python don't allow us, I'm talking about C Python, it don't allow us to capture GIL by 2 threads simultaneously. But we have a preemptive multitasking. We can tune it through serial.git file. In Python 2, the preemptive multitasking stops any process after 100 bytecode instructions. In Python 3, it's 15 milliseconds. That parameters can be tuned. And actually, it's a very helpful feature because when we run some code, we have to block something that goes wrong, and if it takes too long, because if it is not calculated in one time point, it doesn't matter anymore. But also we can do a multi-threading calculation for some heavy calls. When we call third-party library written, for example, in C++, we make a separate thread, and GIL preemptive multitasking does not control it. When we start it, we have no control over it anymore. For example, we are using that approach for a physics engine. All the physics is calculated separately. Also, on the client side, the render is calculated separately on a client machine on the graphic cards. So it's impossible to do in Python, and actually there is no reason to do it in Python. But when we call such function, we have to be sure that it will finish before time quant ends. So to be sure that we have to make a review, we have to make a code gatekeeping, we have to make a lot of performance testing and quality assurance to be sure that in any way that code which is called here will give us response in time less than one time quant. But not everything is so easy. There is some examples of Python heavy calls which is not interrupted by preemptive multitasking. For example, it is garbage collector. When garbage collector works, it is some kind of stop of the world, and the program will continue its working only after garbage collection stops. Garbage collection is some kind of house monkey where it appears and it starts in absolutely random time. We cannot control this. So that's why we have to switch off any heavy calls which can interrupt our real-time maintenance. So we discussed little issues which can appear when we are using Python for real-time application, and let's talk about network performance and network optimization. First of all, network is about sending the packages, and we have to decide what we send and how do we send. First of all, when we design such application, we have to limit the information we send by two reasons. First of all, we have a limited channel, and we have to send only the information that is needed by the client. And the second limitation is a gameplay limitation, because if we send some explicit information to our client may cheat using that information. So we have to limit any packages we send to the client, and actually that is also good for network performance because we send less information. And how do we send? We can send it in reliable, ordered, and error-checked delivery, but actually that delivery is more expensive. Rather than sending just UDP package, non-reliable, non-ordered. So that's why we have two types of packages we send. One of them are important and mandatory for every player, and another packages are not so important for gameplay, so we send them in non-reliable way. Big model entities have three models, and we exchange the model state between different applications. As I already mentioned, we have base application, cell application, and client application, and every entity has three models in three separate processes, but actually it is the same entity. And we share its state through the network between the three applications. Such common parameters and inter-process function calls defined in dev files in Visual Engine. We are using mailbox-based inter-procedure communication, and as you can see, if we have the same entity in the two different processes, we can call directly methods of that entity if, for example, it defined in one process and we have to call it from another process. Also, some bugs can appear because of that reason. Let me explain network communication in more details. Probably when you saw a schema previously, you can have a question why it's so complicated. Here is an example of map. Map is an arena. It is one game session, and we have players on the map. To provide calculation of the gameplay inside, we divide that map into different cells, and each cell is running on their own cell application. The code which is running on one cell doesn't know anything about the code which is running on another cell, but we can exchange its state through a mailbox. Here is how the map looks on the server side. On the client side, maps look like just a 3D model, so client don't know anything about it. Probably client can see that in case of microfreezes between them. Let's look on this example in more details. For example, currently we want to create any entity, and first of all we instantiate that entity in the base app. We can initialize it through some configuration file or through database using the database application. And after that, we share its state through a network to a client application, to cell application, and to other applications which are necessary. As I said previously, we have a lot of cells on the map. So we have one master cell entity and other ghost cell entity, which is shown as a gray figure here, so that if some player plays on different cell, he still can see the object from another cell. That example is quite costly because of that ghost entities. Let's look why. First of all, multi-cell approach allows us to make an infinite scale, and of course it's an opportunity. Also, multi-cell approach help us to load server better because of high fragmentation. We have small cells and we can allocate them into servers so that all servers would be loaded approximately at its maximum. Rather than in case of single cell, if the whole arena would be just one cell, we have some fragmentation issues and some servers have not used computational power. Also, the opportunity of multi-cell approach is a scaling. So if, for example, we would like to make arena 4 times bigger, we just run 4 cells. In case of 9 times bigger, we just run 9 cells. And it not cause any problem. In case of single cell, we are limited by our hardware. So if sometimes if cell appears to be more than it can be processed on the server, we just can't run it. Also, the opportunity of single cell is lower network communication. In case of multi-cell approach, we have a lot of data which should be shared between cells. And actually, that traffic is quite expensive, and it takes quite a long time. And still keep in mind that we have to provide any answer in one time quant. So we have to pack and unpack all the data we send through a network every time. In case of single cell, of course, we don't have such network issues. And the development cost, which means that when we are developing for any feature and any new class or object, we have to keep in mind that we cannot just call its methods through a dot notation. For example, you instantiate an object, then call any method, as usually in any single thread program. But here we have to keep in mind that any object can be on any cell, and we have to communicate it through host entities and through mailbox. So the opportunity of multi-cell approach in that case is unlimited scale. There is no fragmentational issues, but we have network overhead, high development cost, high maintenance cost, and because of high development cost, we have some specific bugs. On a single cell approach, we are limited by maximum hardware capacity, but we have some fragmentational issues, but we don't have any network overhead, and we have lower development cost, lower maintenance cost, and Big World was initially made for infinite worlds, and it's ideal for the world without any borders. Because we are running a session-based game, which map is limited, we decided to switch to a single cell a couple of years ago, and since that we are using that approach. Let's talk about variable types in Python. In usual Python programming, we don't have to care about variable types. We can send, for example, we can make an array of any objects, and we can operate them. But actually, it matters when it comes to a huge and complicated system like that. We have to use variable types information to work in cooperation with other modules. For example, the game engine require the types. Also, database require the types, and other modules which can require types. So we have to provide that information to them. We have to know types to optimize network usage. Also, we have to know types for proper and fast unpacking and using database efficiently. That is a couple examples of database types using a schema. If we have to save something, we have to make a type of that variable. Also in game engine, we, for example, have an account which is also have a type, have some flags, have some persistent options and database length and so on. So that even using Python for the whole cluster, we have to care about variable types inside. Just because when we communicate through different model, we have to provide that information. When we communicate through a network, to optimize that, we also have to provide that information. That is a small example of packer and packer. We have to know the type of variable, and with that information, we cannot just send directly a couple of dicts directly between two Python applications, even if they are both Python, without any man in the middle. So that we provide a packer for any variable which have to be sent. After that, we are using pickle and delete. That also makes some issues because cpickle is not safe, so we cannot instantiate class through an unreliable network using cpickle. For example, we can't use it using an inner internet, and we cannot send cpickle classes to a client, but we can use it inside our intranet between the different applications just to save some network bandwidth. So I hope I described some problems which can appear when we are using Python for a huge and complicated project. Also, when you are making real-time and high-load application, you have to care about a lot of things, such as guild capture control, non-Python call performance, garbage collectors, some variable types. All the issues are solvable, so there is a way to solve it, and it works because the opportunity of using Python allow us to make very rapid prototyping, it makes us to make features faster, so that we can leave our players engaged into the game, just because in the same time we can provide for our players not one, but for example 3 features. And using Python worth it. Thank you very much. Any questions? I will share the slides here.
We do have time for some questions.
Did you consider any of the alternate Python interpreters, such as PyPy or Stackless?
Actually, we are using CPython, but not the stock CPython version, but our modified CPython version. And we cannot use PyPy and other just because of C bindings. The game engine is written in C, and CPython provides by default very good and efficient in performance C bindings. So that's why we have to use it.
Yes?
From your slides, it looks like you're using pickle data transfer formats internally, and then is it Avro or some kind of external networking format? I was wondering if you could kind of clarify what the data exchange policies are and when the boundaries are.
We don't use cpickle for sending in information to client, of course. As I said, it's hazardous. But we have our own format, so that client can get it and read it. Actually, we cannot. We would like to keep that format in secret, of course, but we can't because it's open to the whole internet. And there is a huge community which make client modification, and they try to use that information. They know the format just because they can make some work in previously with our client. So that yes, that form we would like to make to keep that format a secret, but it's impossible, of course.
You referred in the beginning that you have an issue with cheaters in the games.
Cheaters.
Have you thought about placing all the cheaters on their own cluster? So they play against each other?
It's like an Olympic game where all the dopings and other play separately. Well, actually, one cheater can decrease an enjoy of a lot of players. For example, just one cheater can affect 1,000 players just playing simultaneously couple of battles. Because of that, we care about our normal clients, and actually we would like not to allow any cheats, but as you can see, it's impossible not to allow because we cannot control the client's hardware. So that we block the most popular cheats which affect gameplay. But also we have a community which voluntarily make some game modification, but their modification don't influence gameplay so much. Just for example, different color or some additional information on the board. So we have a community of our good modders, and we have to block those who affect gameplay.
One question if I have time. In Arena, you every cell located in local some different machine. What will happen if one machine will die?
Yes, that is a reliability issue which is solved by game engine. The cell application is the huge application with a lot of objects inside. Some objects are persistent, so we have to save its state even we move from one cell to another. It can happen not only because cell up is died somehow, but for example when the server capacity isn't enough, we have to replace it somewhere else. And we have a special mechanism to relocate one cell up from one machine to another, with saving all persistent variables, of course.
I'll have to cut this now because there's another talk starting in the other rooms in 1 minute. But if we could thank our speaker again, and he'll be around to take any questions.